You've most likely heard of or even used the feature that's called Deep Search that is available on all the top chatbots out there like ChatGPT, Gemini, Grok, and Perplexity. But even if you don't know what it is, don't worry. In this video, I will explain it and show you how you can build it for your own chatbot. So basically, this feature allows the user to perform a deep search on the web given a search query. And it's basically an AI agent working behind the scene that can analyze the user query, search the web, collect data from different sources, and even different formats like HTML, JSON, PDFs, and videos. Now, as I said, I will show you how to build your own deep search AI agent and how to integrate it as a tool with any chatbot or LLM that supports tool calling. But first, let me show you a quick example on how it works. So here I built this small chatbot with Streamlit just to showcase that the integration is fairly simple, and you can see that it takes a while to gather information and generate the final response. And once the deep search is complete, you can see the final report, and on the side here we have few statistics about the deep search operation that was performed. So for example, we have the total URLs searched, the total URLs scraped, and the length of the generated report. And you'll see later that it really did a decent job generating a referenced detailed report on the user query, and I will also give you a few tips on how to improve it as well. Alright, so let's get started. So as usual, first I will explain a bit and discuss the approach that I chose to build this AI agent, and then I will walk you through the code and explain it as well. So when I wanted to build this functionality, I first wanted to understand how it works in the current chatbots. So I asked them how do they perform deep search, and their responses were very similar. So here we have the response from the Grok chatbot. And as you can see, I used the deep search functionality when I asked this question. So it generated a long report on how Grok performs deep search. So we're not going to go through the whole report, but briefly what Grok said it does is the following. So the first step is understanding the user question. So the agent they used breaks down the user query to make sure that it gets the key terms, the context, and the level of details required right. The next step is the initial web search for broad information. It basically uses web searching tools with broad query on the topic to gather an overview and locate potential sources. And then the next step is the source evaluation and selection. So based on the previous search results, it evaluates the credibility and relevance of each source and prioritizes authoritative ones like scientific journals and papers. Then the fourth step is the detailed browsing for specific information. Now during this step, it uses browsing tools to access and read through selected web pages or documents and extract detailed information. Then we have the fifth step, the cross-verification for accuracy. So basically it cross-verifies facts across multiple sources to make sure that the final report is more reliable. Then the next step is called domain-specific queries. This is an optional step where the AI agent uses APIs to get specific data like in finance or sports. And then we have the synthesis and presentation of the answer. So here the agent generates a coherent and clear answer with references based on the collected data, of course. And then the final step is iteration for completeness. Now in this step, the AI agent judges the final answer, and if the answer is deemed incomplete or unclear, it refines the search or explore additional sources. So as you can see, this 8-step process can take a lot of time, depending of course on the complexity of the user query and the volume of publicly available data on the subject. However, it surely provides reliable answers, at least based on my own personal experience. And as I mentioned, I asked the other chatbots as well, how do they perform their deep search operation, and their answers were very similar. So now that I have an overview on how to perform these deep search operations, I wanted to create an agent that achieves similar results, but with a simpler approach. And in my mind, I had two ways or two approaches to build such agent. One is fully autonomous and one is hybrid, and let me tell you what I mean by that. So an autonomous agent perceives the environment, decides the next action, execute it, and then update its state, and this course of actions is repeated until a goal is achieved. And as you may know, there are several autonomous agent architectures like reactive agents, goal-based agents, and utility-based agents. And to build our deep search agent using this method, we can use, for example, a carefully designed React agent using LangChain or LangGraph. And the other way is the hybrid approach. So this approach combines a deterministic workflow and the agentic autonomous behavior. This approach allows for more controllability while maintaining a certain degree of autonomy. It is well suited for cases where the whole workflow has parts that needs to be executed each time the agent is called, and other parts involving looping behavior and decision making. Now, most of the deep search tools in chatbots have a similar procedure or process to what we've seen with Grok. And we can safely assume that, for example, the first two steps, understanding the user question and initial web search for broad information, are always performed no matter what the user query is. And for example, with ChatGPT, you can try this on your own. If you ask it to perform a deep search on a certain subject, it will ask you a certain number of questions to better understand what you are looking for exactly. So basically that step is always performed with ChatGPT, and then the next few steps involving searching the web, data gathering and data validation should be performed using an agentic loop behavior. So the loop will continue until the agent decides that we have enough information to generate our final response. And basically that's why I chose to use a hybrid approach. And to better understand it, let me show you in more details the architecture and the steps involved in the deep search hybrid agent that I built. And then I'll show you how to convert all these steps and logic into code. Alright, so here we'll see the whole process for the deep search agent, and I've built it mainly with LangChain. So first, we always do start with a user query. So for example, here we have perform a deep search on how the retail industry has changed in the past 3 years. Now this query will be passed to an LLM that will analyze it and generate a list of questions and queries. So this is a very crucial step that will determine the quality and depth of the deep search, and you will see why in a bit. So first, the agent breaks down the query and retrieves the key terms to make sure that it understands it correctly, and most importantly, that it understands the intentions of the user and what they're asking about. Then it generates a list of questions or sub-questions that needs to be answered to fully address the user query and the topics that were mentioned in it. After that, for each question, we generate a web search query that will be used to gather information. So we have one web search query for each question. Now, about what I said earlier, the number of questions and queries generated will determine the maximum depth of the performed search, because in the following steps, no more web search queries will be generated. This is just a choice that I made so that the deep search functionality don't take too much time, given that with the current settings and with the example query that I showed you, it takes around 5 minutes to complete a deep search. But of course, this is one of many things that can be changed to improve the result and build a better version of the deep search agent. But for now, we generate a maximum of 5 questions and 5 web search queries. Alright, so for simplicity, we will consider that we only have 3 generated questions and web search queries as output of the first step. Then in the next step, we perform web search using Google to retrieve a list of the top URLs for each query. Also, this number is a parameter that can be adjusted as you wish to set the maximum depth per query. And as an output, we will have the generated URLs list. So this list may contain invalid URLs or URLs that point to media files. So we naturally need to filter out the unwanted URLs. So I chose to keep only working URLs that points to an HTML web page or a PDF file. Now the next step is data scraping or data gathering. So we pass the URLs from those lists iteratively to a web scraping and data cleaning component. This component will scrape the URL and produces a clean text containing the most relevant chunks of information to the question or sub-question we're trying to answer. But as I said, we may have URLs that point to HTML pages and others pointing to PDF files. So what I did here is the following. First, I used a Python library called Crawl for AI to scrape web pages and produce a semi-cleaned markdown text. So it basically gets the whole HTML page and removes all the unnecessary tags, then converts it to markdown. This way the length of the scraped text is reduced dramatically, and that's what we want because we will pass that text to an LLM to get the final cleaned version containing only relevant chunks of data. And by the way, Crawl for AI has a built-in LLM extracting strategy. However, when I tried it, it used much more tokens than needed when performing LLM calls. And also it increased the whole scraping process time a lot. So that's why I opted to not use it in this workflow. So basically that's how we gather information from web pages, but for PDFs we need a different approach. So what I chose to do is that I download the PDF file as a temporary file and then pass only the first 20 pages to Mistral OCR API to convert it to a markdown format, and then we use an LLM to clean it, similar to what we did with web pages content. Now this approach involving downloading PDFs, but we have the option to pass the PDF URL directly to the Mistral OCR API. However, we need to be careful because we don't know what PDF to expect. So many times the PDFs are too long and passing it directly to an API could be inconvenient. And sometimes even if the PDF was converted to a markdown, we won't be able to pass it to an LLM since it has a context length limit. So that's why I chose to only perform OCR on the first 20 pages of any PDF we get, and to extract those pages I needed to download the PDF. So basically that's how we gather data from each URL. The next step is data sufficiency judgment, where the agent judges whether the collected data so far are enough to answer the question related to it or not. And in case the data was deemed insufficient, we pass the next URL to the data gathering and judgment process, and the loop continues. Then once it is decided that we have enough information, we pass to the next step, and that is SAB report generation. So for each question we want to answer, we use all the gathered data to generate a referenced and detailed report, or you can call it a SAB report, that will include as much information as it can from the collected data. And this step acts as an information funnel so that later, when we generate a comprehensive and referenced final report, as you can imagine, given the volume of data that can be collected for each question, we can't directly use it to generate the final report, as it may exceed the context length of the LLM used. That's why I thought it would be better to compress it into sub-reports first. And now that we have the referenced sub-reports generated, we can prepare our final report to answer the user query. And this time we pass to the LLM all the sub-reports along with the user query and its breakdown, and get the final referenced sub-report as an output. So basically this is the full process of this hybrid agent. And as I discussed, there are several ways to improve it. And here's one more way that I didn't take into consideration, and that is very important to generate a reliable result. And that is, of course, information cross-checking and validation. And we can achieve that using different techniques. For example, we can prioritize information from authoritative websites or domains. And we can also prioritize information from expert sources like scientific papers, official reports, and known news outlets. And we can also use the agent to flag contradictory information from different sources. And when generating the reports, we can ask it to use cautious language when uncertain. Alright, so I hope the process is clear. Now let's move on to the code. So here we have the notebook that contains the code for the deep search agent. And after that, I will quickly show you the code for the Streamlit app, where, as you can see here, we're running the deep search as a tool. Alright, so first we start with few library installation. As I said, I'm using Crawl for AI to scrape websites. So we need to install it using pip, and then we set it up using this command. And then we need to install LangChain, of course, with the libraries required to create the agent and to make calls for the Gemini API. We also need this library to perform Google search, and the Mistral AI to make calls for the OCR API. And then we need the PyPDF to extract the first 20 pages from the downloaded PDF. And that's basically all the libraries you need to install. So here we have the imports. We import the usual libraries. Then we have a few imports from Crawl for AI and from LangChain. And we're using the Pydantic library with typing to set our structured outputs. Then we set the API keys. So we have an API key for Gemini and API key for Mistral. Now both of these APIs are free, and you can get your own API key and set it here in the Secrets tab. Then we have a few helper functions that we will cover later, but first we have here the agent code. So here you can see the workflow that I've presented earlier. So we start with the user query, and then we use the generate plan function to break down the query, get the sub-questions and the search queries. And let me show you the output for that first. So here's the example output that we get. So we have the query breakdown, and here's the breakdown. Then we have the list of sub-questions, and after that the list of search queries. Next we perform web search. So for each query we get the first or the top 15 URLs from Google search, and we store those URLs in lists. Once we have the URLs for each query, we pass to the data collection phase. So here we initialize an empty list for the gathered information, and we loop over the sub-questions and the list of URLs for each question. Then we create a list where we will store the data for the current query, and we check if the list of URLs is empty or not. And if it's not empty, we scrape the first URL and clean the data we obtain using this function, fetch and clean. And we store the output data in the user query list, and we iterate over all the queries and search results or URL lists. And that's how we collect the data for the first URL for each query. And then we pass to the data validation and supplementation. So we have a list for the accepted data, and we loop over the sub-questions, queries, data list, and URLs. So the URLs contains the URLs for each query or for each sub-question, and the data list contains the gathered info from the first URL we just scrolled or scraped. And then we have the query and sub-question. So first we use this function judging collected data to judge whether the collected data from just the first URL is sufficient or not. So basically this first part just checks whether we have an empty data list or not. And then we start our loop in case the data isn't sufficient. So while not sufficient, and while also the current index is less than the length of the list of URLs. So the maximum number of iteration in this loop would be 15. And we start by fetching and cleaning the next URL. So we get the data and we clean it, and we store it in our data list. And then we judge the collected data. So here we judge the data collected from this URL along with the data from the first URL. So it's cumulative, and we see if it's sufficient or not. And in case it's not sufficient, the loop continues. And once we exit the loop, either by getting sufficient data or by reaching the maximum number of iteration possible, we store the current data list along with the URLs list so we can get the references afterwards in the reports in the accepted data. So these data in this list are deemed as accepted, and we will use them to generate the sub-report. So the next step is to generate a sub-report for each sub-question using the accepted data for that sub-question. And we have a list of sub-reports. And as a final step, we generate the final report. As I said before, we pass the user query, the query breakdown, the sub-questions, and the sub-reports, and we get the final report. So now let me go into details for these helper functions, the generate plan, the fetch and clean, etc. So here we start with the generate plan. So this function gets the user query. So it first initializes a model. Here we're using Gemini 2.0 Flash. And with this system prompt, we're gonna generate a query breakdown, then a sub-questions list, and a search queries list. Now, I didn't write this whole system prompt, I just expressed what I want the model to do, and I used ChatGPT to generate the system prompt. And I actually advise you to create your system prompts using this approach, because the chatbots are very knowledgeable about creating prompts and how to formulate them well so that the model performs in the way we intend it to. So then we create this class. This class is a base model from Pydantic, and we use such classes to impose a structured output on the model. So here we want to get a query breakdown as a string, a list of sub-questions and a list of search queries. And using this method with structured output, we tell the model that we need the output to follow this structure. And behind the scene, this class is converted to a JSON format and is passed to the model along with the system prompt, so the model would know what to do. And then we create our message history. So here we have a system prompt and then the user query, which is this one. And just like that, we call the model and we get the result. The result is then converted to a dictionary format using model dump. And as we've seen, after running the generate plan function using this user query, we get this response. The next function is web search. So this function gets as input the search queries along with the number of results we want to get. And as you can see here, what we're doing is creating a list for the results. And for each web search query, we create a list for the accepted URLs. So first we perform a web search using this function from the library we installed at the start, Google Search Python. And you can see here from Google Search, we import search. So we pass the search query, we indicate the number of results, we set a timeout, and we want only unique responses or unique URLs. Now each URL we get, we pass it to the should skip URL, and this is the filter function that decides whether we accept the URL or not, and it returns the verdict and the URL type. So this variable is a Boolean variable that indicates whether we should skip the URL. So if it's true, it means we should skip the URL. So if it is not true, meaning that we shouldn't skip the URL, then we append it to the accepted URLs list. And that's how we build the list of accepted URLs for each search query, and we return the results. Now the next function is the should skip URL that we've just used. Now I've created this function using ChatGPT, and what it does is simple. It first checks whether the URL has HTTPS or not. And if it doesn't have HTTPS, then we reject it. And that's mainly because we want to scrape only secure URLs. And then it checks in the remaining of this function whether the URL is valid or not, and whether it points to a PDF file or not. And that's basically what it does. So let's move on to the next function, which is the crawl for AI function. So this is an async function because crawl for AI only provides an async web crawler. So we need this function to be async. So what we're doing here is using this web crawler to scrape the content of a URL. So we get a URL as input. And then we run this crawler using a run. We pass the URL and the config. Now the config I chose for this crawling operation has a markdown generator. The scraping strategy is LXML, which is pretty fast for crawling normal websites. And then we don't need to cache, so we set the cache mode to bypass. And for the markdown generator, we ignore all the links, we skip the internal links, and we ignore images. So the output for this scraping or crawling operation would be as I described, semi-clean. We need to further clean it afterwards. And we can get the markdown from the results object as follows. So we get the extracted content. We load it using JSON, and then we get the markdown. And this function will be used afterwards in the fetch and clean function. So here you can see we call the crawl for AI function for the HTML URLs. So the next function is the download PDF function, and it's a fairly simple one that gets a PDF URL and download it given this file name. The next one is extract pages. Now this is also a simple function. We use the PDF reader and PDF writer from the PyPDF2 to extract the first indicated number of pages from a PDF. So here it is initialized to 3. Then the next function is encode PDF. So when passing a PDF file to the Mistral API, we need to encode it to base 64. Then we have the PDF OCR. Now this function calls the Mistral API and pass the base 64 PDF to get the OCR response, basically the PDF in Markdown format. And as you can see here, we first download the PDF, we create a shortened PDF path, and we extract the first pages from the PDF. And here, as you can see, the page count is set to 5. The next function is clean scraped data LLM. As I said, once we get the data from crawl for AI function, it is not really clean data. Also, the data from the Mistral API, it is not really clean. We only want to keep relevant information, and that's why we will use this clean scraped data LLM. It follows a similar structure to the generate LLM we've seen earlier. So you can see we initialize the model, we create our system prompt, and then we call the LLM using a structured output. And here as well, you can see we initialize the model, we create the system prompt, and we create our structured output base model. And then here I created this simple logic where if we have the scraped data too long, we pass it by chunks to the LLM so that we don't exceed the context length, and we give the LLM the opportunity to focus on smaller text, and that's usually better. So here we create the chunks list, and we set the paragraph size to 20,000 characters. Next, we calculate how many paragraphs are there in the scraped data, and then we pass those paragraphs one by one to the LLM, and we extend our chunks list. And finally, we concatenate the chunks into a clean content string, and we return that string. So the next function is fetch and clean. It gets the URL info and the sub-question. The sub-question is needed in this function we've just seen, so that the LLM decides whether the data is relevant to that sub-question or not. And that's how we get information relevant to that sub-question. So here in this fetch and clean data, we first check whether the URL is for HTML or for PDF file. If it's for HTML, we call the crawl for AI function, and then we clean the scraped data. And in case it is a PDF file, we perform PDF OCR. We concatenate the scraped data and pass it to the clean scraped data LLM and return the clean content. Now, the next function is the judging collecting data function. This function is used to judge the collected data either to be sufficient or not. So it gets as input the gathered info or gathered data, the sub-question and the query, and it tells us whether the data is enough to answer the sub-question thoroughly or not, and returns its judgment here. So the next function is the sub-report generation. And this function is used to generate the sub-reports using the accepted gathered data. This time we're using the Gemini 2.5 Flash for better thinking and better report generation. And here the accepted gathered data contains the data with the list of URLs that were used to gather that data. So the report we generate is actually referenced. So as you can see here, we're indicating that whenever you use specific information from a chunk, include its reference in brackets immediately after the fact. And here as well, each time you reference a chunk, use its exact reference tag with the URL. So source A URL. That way we keep track of every information with its reference. And finally, we have the final report generation function. We have the system prompt here, and we use the sub-reports concatenated along with the query breakdown and the original user query to generate the final report. Alright, so that's how the agent is created. One last thing is converting the agent to a LangChain tool. So basically we create this asynchronous function. We need it to be asynchronous to be able to run the crawl for AI scraper. And then we wrap it using this tool decorator. We give it a description and an argument schema for the input. And now this function is ready to be used as a tool in a LangChain agent or chatbot. And let me show you here in the app. So we import the run deep search. Let me show you the run deep search from the tools. Here we have the same run deep search. This is the same function, except that I added a few things like printing for debugging and this deep search summary to show in the UI the stage of the deep search operation. And that's basically the same thing. Then we return the statistics that I showed you at the beginning of this video. Now here that run deep search is used as a tool for this given model that will be converted to a chatbot. So we only have one tool, and you indicate in the system prompt that if the user asks for a deep search, so here you have access to a special tool called Deep Search Tool, which can perform in-depth investigation on a topic. Only use it when the user explicitly requests a deep search or using the trigger word deep search. And that's basically it. Then you can create a simple UI using Streamlit for the chatbot. And let me show you how it works. So Streamlit run app.py. So here we have the web app. You can talk with the chatbot from here. And here you have a few information about this deep search chatbot. Let me copy, for example, this query. Let's run it. So it is asking me, are you sure you want to perform deep search? Let me say yes. And as you can see, the operation started. It is now searching the web to get a list of URLs for each web search query. And this whole process will take a few minutes, so I will speed it up. Alright, so now we have the final report generating. And as you can see, it is very detailed with all the used references. And finally, we have the list of references used. Now we have this button that you can use to download this generated report in Markdown format. And if we go up, you can see here we have some statistics. We have the total number of sub-questions generated, the total number of URLs searched and scraped, and then we have the total number of useful data chunks, and the average length of the generated reports. And then we have the logs for the different steps taken in this operation. So we have the query breakdown, the sub-questions, the search queries, and then the web search results. And after that, all the remaining steps logs in here. So let me show you when we download the generated report. You get it in Markdown format, and if you open it, you can get it here. And let me show you the preview. And here you go, you have your final generated report. And basically that's it for the deep search agent. Alright, so that's it for this video, and I'll see you in the next one.